This is a video assignment for CHE 61504 Engineering Fluid Mechanics. The assignment title is Properties of Fluid, Non-Newtonian Fluid, and Application of Continuity, Bernoulli's, and Momentum Equation. We are Group 6, and here are our details. We are of the March 2021 semester here at Taylor's University. As we proceed, please feel free to pause the video at any moment to further understand the details.
Hello, my name is Nurullah. We're going to start with the properties of fluids. Please feel free to pause the video at any time to have a look at the definitions in detail. First, we have mass density, which has the unit of kilograms per cubic meter. Next, we have specific weight, which has the unit of newtons per cubic meter. Then we have the specific volume, which has the unit of cubic meter per kilogram. We have the relative density. We have the compressibility, which is when a pressure is applied on a fluid, the volume naturally decreases, which relates to the elasticity, that when this pressure is released, the fluid should return to the original volume. Then we have the vapor pressure, the surface tension, which is a force that makes the liquid or the fluid form a layer at the surface and is caused due to the cohesive force between the molecules of the fluid. Then we have the capillarity and the buoyancy, and finally we have the viscosity, which is the most important thing. It is the measure of the resistance of the flow of fluids. It's very important because this is what differentiates Newtonian from non-Newtonian fluids. In Newtonian fluids, they have a constant viscosity that doesn't change no matter the pressure being applied to the fluid. We're going to discuss the non-Newtonian fluids. They are homogeneous, they resist flowing, but the main difference between them and Newtonian fluids is that the non-Newtonian fluids can change their viscosity. When does that happen? This is when they are under stress. If there's a force applied to these fluids, for example, if you hit them or shake them or jump on them, the sudden application of this type of force or stress can cause them to become thicker and act like a solid. These are called dilatants. Or they can result in the opposite behavior, and they may become faster than they were before. These are called pseudoplastics. As soon as the tension that has been exerted on them is removed, though, the fluids will return to the previous state.
Hello everyone, I'm Hao-Wing. The example of non-Newtonian fluid we are going to use today is shampoo. So, why shampoo is a non-Newtonian fluid? It fulfills the criteria of shear thinning. What is shear thinning? Shear thinning is the non-Newtonian behavior of fluid whose viscosity decreases under shear strain. Here shows a shear rate versus viscosity graph of shear thinning.
Hi, I'll be showing the viscosity of a non-Newtonian fluid, which is the shampoo I'll be using, and I'll be showing the viscosity of both, one being shaken and one not being shaken. So before the experiment begins, what I'm expecting is the shaken shampoo will flow faster than the non-shaken shampoo. So how am I going to do this? I'm going to take a clear sheet, something like this. I'm going to draw a line on the clear sheet. I don't know if you can see it, but it's like right over here. So this will be the starting line, and I will see which flows faster. Okay, firstly I'll add the shampoo which is not shaken. So here's the shampoo which is not being shaken, and now I'm going to shake the shampoo vigorously, and then I'm going to add a kind of the same amount of shampoo and see how both flows. So as you can see from here is the shampoo being shaken, and here's the shampoo not being shaken. So let's test which will flow faster. As you can see, the one being shaken flowing faster compared to one not being shaken. And from here, as expected from what I said in the beginning, the one being shaken will flow faster than the other one. So here we can see a shear thinning process of a shampoo. Thank you.
From the experiment that was conducted, we are able to observe that shampoo goes through a shear thinning process. And from this graph, as shear rate increases, the viscosity of the shampoo decreases in value, which proves that shampoo goes through a shear thinning process. And on this graph on the right, it is similar to the pseudoplastic fluid, which proves that shampoo is actually a pseudoplastic fluid. I'm Adriel, and I will be briefing you through the experiments and also to tell you more about the apparatus that we will be using in this experiment. So first of all, we are going to use the application of a 1 liter milk box for our assignment. So what is interesting about this is that there is two parts in this cylindrical tube. There is the internal part, which is the neck, and also the spout. So the neck actually has a smaller diameter as compared to the spout. So with the difference in diameter, we are actually able to find out different pressures at different points. And here we have a blender that has its own volumetric labels on it. And I've also placed a ruler here onto the wall, which measures up to 30 centimeters. And here I have a sticky note that actually labels the 30 centimeters for better indication. And lastly, I'll be using my iPad as the stopwatch for this experiment. This is the milk box that is of 1 liter in volume, and it can be observed that when liquid is being poured out of the box, the fluid flow is not smooth. This is because when the liquid exits the box, it creates a low pressure region in the box. And when there is low pressure in the box, it will suck in air through the spout and cause a disruption in flow, which is not ideal for this experiment. So what we've done is to actually balance the pressure in the box and also with the surrounding. And in order to do that, we have actually punctured a hole at the bottom of the box to ensure that when fluid is being poured out, there is no disruption in flow due to the difference in air pressure. Okay, this experiment is conducted to find the value of velocity at point 2, which is V2. So in order for us to find V2, we must actually find the time taken for the water to travel at the distance of 30 centimeters until the bottom of this accumulation tank. So with that time taken, we can take 30 centimeters and divide the time taken, and we can find the velocity at point 2, which is V2. As soon as I release my finger, I will start my stopwatch, and as the water hits the bottom of the tank, I will stop the stopwatch. 3, 2, 1, go. Okay. So from the stopwatch, we can see that the time taken for the water to travel is 0.36 seconds. In this experiment, we are going to find out the value of volumetric flow rate. So in order to find volumetric flow rate, we are going to obtain the time taken for the water to accumulate from 0 until 1 liter. So in order to do that, I'm going to place the milk box that is filled with 1 liter of water at an elevation of 30 centimeters, and as soon as I release the water into this accumulation tank, I will start my stopwatch, and as soon as the water level reaches at 1 liter over here, I will stop the stopwatch. Okay, we will start in 3, 2, 1. Stop. Okay. So here we have the time, which is 6 seconds, 0.74. So this is the accumulation tank that has been filled with water. It says here 1000 ml, which is 1 liter. These are the apparatus and materials used in the experiment. Firstly, the blender machine, ruler, 1 liter milk box, water as our working fluid, and stopwatch. So here is a figure of the spout and also the neck, and we can see that it has different diameters, and they are labeled as D2 and D1 respectively. So here Z1 is equals to 0 because it is our datum point, and Z2 is at an elevation of 0.7 centimeters. And here we have a picture of the transparent neck that has been detached from the milk box. So this is a schematic figure of the experiment that was conducted here. And this is a zoomed in figure of the spout area. And this will be our control volume, and we will obtain all of the variables here. So here are all of the labeled details listed out for you. And we are able to know that 1 liter of water is actually equals to 1 kilogram. And with the mass, we are able to find weight by multiplying it by gravitational acceleration. And weight is also equals to force, and therefore it is 9.81 newtons. With the force, we will find pressure at point 1 using the formula, and this is the value for P1 that can be applied for actual and also theoretical P1 value. So from the experiment, we have time taken, and we can find the theoretical velocity at point 2. And with the value of V2t, we can find the theoretical flow rate by using continuity equation. On the other hand, we can find the actual flow rate by using the volume in terms of meter cube and divide it by TV obtained from the second experiment. So with that, we can find the value and then put it into the continuity equation to find the actual velocity at point 2, V2a, and this is the value. So the percentage error between the actual and theoretical flow rate is 53.16%. So the factors affecting the errors will be turbulent flow, friction between walls and the water, no proper equipment to hold the box at a fixed position at the height of 30 centimeters. Fourthly, there is no proper tool to shut the spout tightly, which contributes to water leakage. Lastly, the start and stop time has slight errors in terms of a few seconds because it is timed manually. And with both the theoretical and also actual flow rate being found, we can find the theoretical velocity at point 1 and the actual velocity at point 1. So by applying once again with continuity equation, we can find both values. And we can put all of those variables into Bernoulli's equation and find out the pressure, the actual pressure at point 2, which is this value, and doing the same thing to find out the theoretical pressure at point 2, and this will be the value. And as you can see, the difference is not that much due to the factors affecting the errors between actual and theoretical pressures.